Let us now look at capacitive network. That is, we have a circuit that is made up of capacitors. And the capacitors can be arranged either in parallel or in series. This figure A is the arrangement of capacitors in parallel. You can see that all the capacitors C1, C2, C3, they have common points. This point is called a junction. Is that okay? It's a principal node, a principal junction. Look at, they also met at this point B, right? Good. For series arrangement, you have figure B here. You can see that the capacitors, they don't have a common point. They don't. Is that okay? They have two different terminals. And what should we know about capacitors when they are arranged in parallel and when they are arranged in series? First, let's analyze that of parallel arrangement. When capacitors are arranged in parallel, they have equal voltage. They have equal what? Voltage. But what about the charge in them? The charge in them is different. And that is why to get the total charge is going to be the summation. You add the charge of each of the capacitors. Look at it here. To get Q is equal to Q1, Q2, plus Q3, plus Q4, down to plus Qn. Now, we know that charge is equal to C times V. Yes, that comes from the equation C equal to Q over V. Is that okay? So if you cross multiply, you're going to get this. Since we know that different charge, okay, exists for parallel capacitors, we're now going to walk from that charge direction. We'll go to the charge and then substitute CV. In place of this Q, we'll put the total capacitance, that is the effective capacitance of these parallel capacitors, times the total voltage, equal to, in place of Q1, we'll substitute C1V1. But you take note that I didn't put V1 here again. Why? Because for parallel arrangement, they have the same word, voltage. Which means that V1 will be the same as V2, it will be the same as V3, it will still be the same as what? V. So that's why we have C1, V1. The same thing here, in place of Q2, we'll have C2V, Q3, C3V, down to Qn, it will be Cnv. Take note, the same voltage. Now looking at the right hand side of the equation, you can factorize voltage from that term. If you factorize voltage from there, you cancel that on the left hand side. So what can we say? Equation 1 simply tells us that if you are to obtain the effective capacitance of parallel arranged capacitors, simply add up the capacitance of each of the capacitors in the circuit. That's all. Add them up, okay? Now, what happens when the capacitors are arranged in series? What should we know about that? Now, we should know that they have different voltage, but the same charge. And because they have different voltage, that is why the total voltage will be equal to the sum of the individual voltages across the capacitors. Right? So for this, we are going to walk from the direction of the voltage now because it's voltage that is different for series arranged capacitors. So what do? Once again, we'll come to this equation and then make V subject to the formula. From here, you know that V is going to be what? V is going to be Q divided by what? C. So we'll come into this equation and then substitute for V, which is Q over C. So let us do that. Since V is equal to Q over C, coming over here, in place of this V, total voltage, we're going to put total charge divided by total capacitance. That is the effective capacitance for series arranged capacitors. And that's going to be equal to, in place of V1, I'm going to put Q1 divided by C1. Once again, take note that I didn't impute anything subscript 1 for the charge 1. Reason, Q1 is the same as Q2, it's the same as Q3, and it's the same as what? Q. Look at that here. So I just have to fix in Q, then plus, in place of this V2, you have Q over C2, plus, in place of V3, you have Q over what? C3, down to plus Q over Cn. Then once again, if you look at the right hand side of this equation, charge Q is common, so you can factorize it out. Look at it. That will cancel the Q that you have on the left hand side. Take note, this Q over C is the same as Q times 1 over C. Is that okay? And once they cancel out, we now have equation 2, 1 over C equal to 1 over C1 plus 1 over C2, down to plus 1 over what? Cn. So what does equation 2 tell us? When we have series capacitors, all we need to do to get the total or the effective capacitance of that circuit, you're going to take the inverse, alright, the reciprocal of each of the capacitances, add them up, and make it equal to the reciprocal of the effective capacitance that you are seeking for. In the next video, we are going to pick questions and then solve for these. We now want to look at the energy stored in a capacitor. When charging a capacitor, you know that you're doing work. And this work appears in the form of energy stored in the capacitor as a result of the charge that the capacitor stores. Now we can derive this energy equation, right, the energy stored in the capacitor, by recalling the fact that our work, that is electrical potential energy, is that okay, which also is work, is equal to QV, charge times voltage. Now I can write this in terms of differential coefficient, del W, that is a little increment in the energy storage, and del V, the little increment in the voltage. Is that okay? Then we can get this equation, del W equal to Q del V. We have already established that capacitance of the capacitor is equal to charge divided by what? The voltage. So in place of this capacitance, in place of this charge, we can cross multiply this equation actually and get CV to be equal to charge, which we substitute and you have CV del V. Now if we transform this to dV, that will give us room to integrate this equation. You can see that. Now we're going to integrate from the initial value of the voltage to a given value of the voltage during the charging process. Because you know that the voltmeter reads the voltage, is that okay? That's being given out as a result of the cell that is used in charging the capacitor. So we're going to integrate from 0 to a given value of voltage V. Now capacitance of the capacitor C is a constant, so it's going to come out of the integral sign. So we integrate V with respect to V. That dV that is telling you what to integrate with respect to. Now this is V raised to power 1. To integrate it, use power rule of integration. Simply add 1 to the power and divide by the new power. Now this is V raised to power 1. If you add 1 to it, you get V raised to power 2. The new power is 2 now, so you divide by what? 2. Enclose the square bracket and then put your limit from 0 to what? To a given value of the voltage V. What do you do with the limit? You substitute the limit for the value of voltage you got here. So in place of this voltage, we're going to put upper limit, which is V. So it's going to be C in brackets, this V, which you substitute this V for. So V squared, look at it. Then minus, come back to this again. In place of this V you obtain during the integration, substitute the lower limit 0. You get 0 raised to power 2 divided by this 2. Now this minus 0 raised to power 2 part, will disappear because that 0 divided by any term is 0. So you'll be left with 1 over 2 CV squared, which is this. So this, the energy stored in a capacitor in terms of the capacitance of the capacitor and what? Voltage. Now if we substitute for this capacitance of the capacitor using Q over V, you see, capacitance of the capacitor C is equal to charge over voltage. So we can substitute for this C here using Q over V. If we do that, this voltage will cancel one of the voltage from the numerator. The formula will become 1 over 2 QV. You can also go further. In place of V, substitute Q over what? C. Look at that. If you make V substitute formula here to be Q over C. So if you substitute for this V as Q over C, this Q will multiply this Q to give us square of the charge divided by what? Capacitance. So equation 1 star, 2 star, and 3 stars are equations, formula used for calculating energy stored in what? In a capacitor. Is that okay? Now in the next video, we're going to take questions and all we've learned and formula established under capacitor and solve them. We now want to look at our very first question on board here. Two concentric spheres of radii, 5 cm and 8 cm, carry charges of plus 3.2 times 10 raised to power minus 16 and minus 3.2 times 10 raised to power minus 16 coulomb respectively. Find the capacitance of the system. Now, you see the question, the spheres are concentric. It means they are coaxial, alright? They have a common center. And that's the diagram I try to bring out here. So, okay, now from the question, these are the information given to us. We know the charge 1, charge 2. We are asked to find the capacitance of the capacitor, which of course, you know, to obtain capacitance of the capacitor, we know that capacitance of the capacitor is equal to charge divided by what? Voltage. That's potential difference. But we also know that for a system like this, where you have two or more charges, to obtain their potential, we can use the equation that the total potential is equal to the sum of the individual potential provided by each of the charge in the question, okay? So all we need to do is to obtain our V, that is the potential, electrical potential. Once we obtain the potential difference there, all right, so we can substitute into the capacitance. But how do we get the potential difference? You would recall that the formula is 1 over 4 pi A naught, all right, times charge divided by what? The distance, that is radius. Now we are going to write V to be equal to, now let us write the formula for V1. Of course, it's going to be 1 over 4 pi A naught times plus Q1 divided by R1, and that will be, you add it to the next potential, that's 1 all over 4 pi A naught, the next electrical potential difference, times that charge. You know, if you're calculating the electrical potential difference, all right, you are meant to use the sign attached to the charge, and that sign is minus Q, minus 3.2 there. So you divide by R2. So if you look at these, the charges in terms of the magnitude, Q1 and Q2 are equal. Is that okay? So you can factorize it in terms of their magnitude, their size, they are equal. You can see that it's just differences in sign. Then 1 over 4 pi A, now that constant is also common, so we can make a factorization to this. In place of this Q1, Q2, I will use Q. So that I'll factorize Q and this 1 over 4 pi A naught. Does that make sense? Open bracket, 1 over R1 will be left here, then minus this term 1 over R2 will be left. Take note that the arrangement of this difference in distances is such that the first distance is that which has the smaller value. Is that okay? And the second has the greater value. So like this R1 will be representing the 5 cm, that's for charge 1, then R2 the 8 cm. And of course, you know we need to convert those to meters by dividing 5 and 8 by 100. So let us substitute into this equation now and see what we are going to arrive at. 1 over 4 pi A naught is the constant, which is equal to 9 times 10 raised to the power 9. Then the value of the charge in terms of the size is 3.2 times 10 raised to the power minus 16. Now open bracket. For the distances, you have 1 all over, R1 is 5, so we're going to write 5 over 100, okay, because you need to do that conversion to solve in SI unit. Then the second 1 over 8 divided by 100. Is that okay? So if you punch out your calculator on this, you're going to get this value. Every time here will give us 216 times 10 raised to the power minus 7. That's what we're going to get, voltage, which of course you can standardize further. Move your point from the front of this 6, 2 times 1, 2, so that the point will appear between 2 and 1. And if you do that, that will give us R. Okay, let me use black marker to write the R term here. So R, this would be 2.16 times 10 raised to the power. You know, if you are moving point to the left, you add to the powers. The number of times I move the point is 2 times. So if you add plus 2 to minus 7, you'll get minus what? 5. Okay, so we shall be using this value 2.16 times 10 raised to the minus 5 is the potential difference of this system. Now let us obtain the value of the capacitance now. It implies that capacitance, which is equal to charge divided by the potential difference, is equal to the charge. We're going to pick one of the charges here, which is 3.2 times 10 raised to the power minus 16, irrespective of the sign. You have nothing to do with the sign here to calculate capacitance. Then divided by our voltage. The voltage, that is potential difference calculated, is 2.16 times 10 raised to the power minus what? 5. Now, if you punch this out in your calculator, let's see what this is going to give us. First, I would divide 3.2 by 2.16, and from here, it's giving me 1.48, then 1.4 something, approximately 1.48. That's going to be times 10 raised to the power. By indices, this minus 5 will go up to become plus 5 with this 16. So you have minus 16 as power plus 5, which is going to give us minus 11 farad. Farad. You know, farad is the unit of capacitance of a capacitor. Now, I want us to obtain this unit in order, this value in other unit of capacitance, like the microfarad and the picofarad. Picofarad is when you have times 10 raised to the power what? Minus 12. And to obtain that times 10 raised to the power minus 12 here, how do we do that? Now watch. I'm going to move this point one time to the right. If you're moving points to the right, you minus from the power. So if I move this point once to the right, I'll subtract 1 from this minus 11. So that's going to give us 14.8 times 10 raised to the power minus 12 farad. Now, that minus 12 farad is going to be 14.8. This 10 raised to the power minus 12 is pico-P farad. Does that make sense? Let's go again. We continue with the R term. Now I want to get the result in microfarad. The micro is times 10 raised to the power minus 6. Now how do we obtain times 10 raised to the power minus 6 from here? I will split this term to 1.48 times 10 raised to the power. Now look at this term. I'll break this power 11 to power 6 and to power 5 and power 6 and power 6. You know, by indices law, 10 raised to the power 5, power minus 5 and times 10 raised to the power minus 6. You pick one of the terms and then add the power, you get minus 11 here. This again in farad, and then if you work that out, or you can now see that the capacitance will give us 1.48 times 10 raised to the power minus 5. This 10 raised to the power minus 6 is now your micro. So it becomes microfarad. So any one of these results from here would give us our answer. Is that okay? Depending on the units that you want to leave your result in. And now we have this question on the board. We are to calculate the combined capacitance of the capacitor arrangements below. This is the arrangement, okay? So we are to obtain the effective capacitance, the total capacitance, all right, the combined capacitance. Now if you look at this arrangement, these capacitors are arranged in series because they do not have common point. All the capacitors did not meet at the same common point. They are joined end to end, all right? Now for series capacitors, you would recall in our previous videos that when capacitors are arranged in series, to obtain the combined capacitance, you use the formula 1 over C equal to 1 over C1 plus 1 over C2 plus 1 over C3 plus 1 over C4. It continues to plus 1 over Cn depending on the number of capacitors you have in a given arrangement or circuit. So in this case, we are summing up to 1 over C4 because there are 4 of them. So it implies that 1 over the combined capacitance will be equal to 1 over C1 is 1 microfarad, and then C2 is 2 microfarad, 1 over C3 is 3 microfarad, and then C4 is 4 microfarads as given from the question. So at this point, we can solve. Either you find the LCM of this term, or you can divide individual terms. I want to divide individual terms here. Then I'm going to get 1 over 1 is 1, plus 1 over 2 is 0.5, then plus 1 over 3 will give us 0.33, then 1 over 4 will give us 0.25. If you add up this, you would obtain that 1 over the combined capacitance is going to give us 2.08. And you know that this 2.08 is numerator, so it's going to be over 1. At this point, if you feel like cross multiplying and then making C subject to the formula by dividing through by 2.08, which is going to be the coefficient of C, that is your choice. But you can still choose to invert. Since this is 1 over C, you can turn it upside down, right? And this is 2.08 over 1. You can also invert. I'm going to use the inversion method. If I inverse, it's going to be C over 1 equal to 1 over 2.08, which implies that the combined capacitance C will now be 1 over 2.08. Okay, if you work it out, 1 over 2.08 from the calculator is giving us 0.48 approximately. Since these capacitors are in microfarad, this will also be in microfarad. So these are our results. Or if you want to get it in farad, so you can say or C is equal to, recall that micro is 10 raised to the power minus 6. So this is the same as 0.48 times 10 raised to the power minus 6 farad. So either of these results is our answer. Now please, I would like you to verify that from this formula, that is 1 over C equal to 1 over C1 down to 1 over C4. Verify by solving this part of the formula using LCM that you could have calculated this capacitance directly. So verify that for this problem, that you could have obtained C directly with the formula C, okay, look at C1 times C2 times C3 times C4, all right, all over C1 times C2 times C3 plus C1 times C2 times C4 plus C1 times C3 times C4, then plus C2 times C3 times C4, okay? Can use this formula directly to obtain the same result as we did. Verify that. We now have this next question on the board to calculate the combined capacitance of the capacitor arrangement below. And this is the arrangement of the capacitor. And if you look at this capacitor, you notice some points that they are arranged in what? In parallel. Okay? Like this point between these, let's fix here to be point B, and then here to be point C. Let's call this to be point D, and this to be point E. Between points B and C, the capacitors we have there are arranged in parallel. So to solve this problem, all I need to do is to take note of these capacitors between points BC. Okay, I can call it CA. As okay, these are parallel capacitors, parallel. Then again, we have this between these 2 points, point C and E. That is point D and E. I'm going to call the resulting capacitance from here to be CB. Again, you notice that they are parallel. Okay? So I will obtain the total capacitance here, which is CA and CB. They will now be connected in series to this 3 microfarad and this 3 microfarad. So this is what we are looking forward to. We want to get something like this, where this is going to be point A, point F, 3 microfarad, CA, CB, and then 3 microfarad. So let us obtain CA and CB first. First, obtain CA and CB. Now you know that CA and CB, for CA, look at it. So CA will have parallel capacitors there because they are in parallel. So for parallel capacitors, CA is going to give us the capacitance of the 2 microfarad plus that of this 2 microfarad plus capacitance of the other 2 microfarad. This is between point B and C, between point BC. So if we do that, our CA will be equivalent to 2 plus 2 plus 2, because I have the 2 microfarads in between these 2 points, which is 6 microfarads. We've gotten our CA. We'll do same to obtain CB. So we also say that CB will be equal to capacitance of the 3 microfarad plus capacitance of the 2 microfarad connected in parallel between point DE. And this is between point D and E. Alright? Between point D and E. So parallel capacitance, which results from the CB, is going to be 3 plus 2, which gives us 5 microfarad. You take note that what we now have is, we now have a diagram that looks like this point A, 3 microfarad. Then this is CA, which we've obtained to be 6 microfarad as calculated. Then CB, which is equal to 5 microfarad as calculated. And then our 3 microfarad and at point F. So this now is series connected capacitors. So series capacitors, we know that the formula is giving us 1 over the effective capacitance, that's the combined capacitance, equal to 1 over capacitance of this 3 microfarad plus 1 over CA plus 1 over CB plus 1 over capacitance of the last 3 microfarad. So if we substitute here, we'll have 1 over C equal to 1 over 3 plus 1 over CA is 6 plus 1 over CB is 5, then plus 1 over this capacitance, which is 3. I'm going to use the LCM method to obtain this. LCM of this denominator is 30. Okay? 30 divided by 3 will give us 10. 10 times 1 is 10, then plus 30 divided by 6 will give us 5. 5 times 1 is 5. Plus 30 divided by 5 is 6. 6 times 1 will give us 6. Then plus 30 divided by 3 is 10. 10 times 1 will give us 10. If you work out this, it implies that 1 over the combined capacitance will give us the numerator. If you add it up, is 31 over 30. From here, we can now invert. Is that okay? We'll do an inversion so that C, it implies that C is equal to 30 over 31. Therefore, the combined capacitance for this arrangement there is going to give us 0.97, that is 30 divided by 31 microfarad. And this is our result for this problem. Just look at what we did. First of all, obtain the resultant capacitance for these three connected parallel capacitance. Obtain also for this, which we call CA and CB. You get this series arrangement, look at it, then use our series capacitor formula to now obtain the overall capacitance of the diagram on board. In this video, we have a question on the board that we are to solve. Okay, it's based on capacitors. And the question is, a parallel plate capacitor of surface area 5 times 10 raised to the minus 4 square meter is connected to an external voltage of 240 volts. If the separation of the plates is 4 centimeter, calculate the 1 capacitance, 2 charge, 3 total energy stored in it. Now I have the second part of the question where it was stated that if the separation is then filled with mica of dielectric constant 7, calculate the new capacitance and energy stored by that capacitor. We are given the value of permittivity of free space, 8.85 times 10 raised to the minus 12 square coulomb per Newton per square meter. Of course, that unit is the same as the farad per meter. How do we approach this question? You can see the distance given to us has been converted to meters. Look at the data, the area, okay, the voltage. Now, in the first part of the question, we want to take note of the fact that the dielectric material filling the space between the two parallel plates was not stated. We weren't told that this is a particular dielectric material that is filling the space of separation in the first part of the question. Hence, we are going to take it that the space between the two parallel plates is vacuum. Or you can say it is filled with air. If it is filled with air, you know the dielectric constant for air is taken to be approximately 1. So it will now approximate toward that of vacuum. Which in that case, we use the formula C to be equal to E naught times A divided by what? D. And that will now give us, by substitution, our E naught is 8, that is permittivity of free space time, 8.85 times 10 raised to the power minus 12 times the area, and the area is 5. We're going to divide it by the distance, which is 0.04. This 0.04 is the same as 4 times 10 raised to the power minus 2. Place the area is 5 times 10 raised to the power minus 4, okay? So we're going to press this with our calculator and get the value of the capacitance. So let us do that and see. I'm going to press 8.85, then multiply by 5 first, okay? So that is 44.25. I'm going to divide it by 4. It's giving me 11.062, so I'm going to approximate to 11.06. Then times, I can now work around the base 10 numbers, alright? This is 10 raised to the minus 12, this is 10 raised to the minus 4. Pick one of the 10, alright? And then add their powers. If you add the powers, minus 12 plus minus 4, which will give us minus 16. Then this minus 2 will go up to become plus 2. Minus 16 plus 2 is going to give us minus 14 farad. This can be written in other units of capacitance, which is equal to 11 points. Okay, now I want to move points, okay? So I want to move point 2 times to the left so that I can add to the power. If you move this point 1 and 2, it will come here, so you have 0.1106 times 10 raised to the power. The power, you're not going to add the 2 to it. The 2 times you move to the left. If you add 2 to minus 14, you get minus what? 12 farad. And of course, this is the same as capacitance to be 0.1106 picofarad. Take note that 10 raised to the power minus 12 is the same as what? Pico. So any 3 of this is the capacitance of this capacitor under the first case. We're going to take a break. When we come back, we'll calculate the charge, alright? Recalling that capacitance of a capacitor is charge divided by what? The voltage. You're welcome from the short break. Now I want to obtain the charge and total energy stored in the capacitor. Okay, so still dealing with the first part of the question. When the space between the plate was filled with vacuum. And before the break, we obtained capacitance to be equal to 11.06 times 10 raised to the power minus 14 farad. We are to calculate the charge in this case, and we know the voltage, alright? So it's given 240 volts. So we're going to recall the relationship between capacitance of a capacitor, charge and voltage. So we know that the capacitance is equal to charge divided by voltage, which implies that the charge is capacitance times voltage by cross multiplying here. Now we're going to substitute to get a charge, alright? So the charge will be equal to capacitance, which is 11.06 times 10 raised to the power minus 14, we shall multiply by the voltage, which is 240. Now let us reach out for a calculator and see what this will give to us, okay? So 11.06 times 10 raised to the power minus 14, so we're going to multiply by 240. Alright, so it's giving me 2.65, approximately 2.65 times 10 raised to the power minus 11 coulomb. So this is the value of the charge stored by the capacitor. Now we're going to obtain the total energy. The total energy, which is the third question to the first part. We know that energy stored in the capacitor is 1 all over 2 CV squared. In terms of capacitance of the capacitor and the voltage, we can still obtain it as 1 over 2 Q squared over what? C. We can also get it as 1 over 2 QV. And of course, I'm going to use this part of the formula, 1 over 2 QV. I don't want to do anything that will lead me to go in square. But you can still use any one of these two, you'll still get the same result. So, I'm going to say that energy is 1 all over 2 times charge times voltage. And the charge already we obtained to be 2.65 times 10 raised to the power minus 11, we shall multiply by the voltage, which is 240. Once again, let's reach out for our calculator and see what this is going to give to us, okay? So I'm going to multiply 2.65 times 10 raised to the power minus 11 by 240, and then I will divide it by 2. So from here, it's giving me 3.18 times 10 raised to the power minus 9 joules. Alright, so this is the energy stored in the capacitor. We are going to take a short break. When we'll come back, we'll focus on the second part of the question. When the space of separation between the two parallel plates was filled with mica of dielectric constant 7. We're going to see what will be the new capacitance and energy stored in that capacitor. You're working from the short break. Now I want to look at the second part of this question, okay? The part where the space of separation between the parallel plate was filled with a dielectric material, which is mica. From this second part of the question, we're given the dielectric constant of mica to be 7. That is the permittivity, relative permittivity of the dielectric material was given. So in obtaining the fourth and fifth part of our question, so it's going to be IV. Capacitance, we don't know. When the space is filled with a dielectric material of relative permittivity, otherwise known as dielectric constant of 7. Okay, now you know that in a case like this, where a particular dielectric material is used to fill the space between the plates. Now, the capacitance formula will be given as the permittivity of that dielectric times area divided by what? This is the general form, you know, where this is permittivity of the material. For air or vacuum, it's equal to E naught, alright? But in the case of mica, now this term, but we know that this is equal to E naught times Kr. That is permittivity of free space times the dielectric constant, otherwise known as relative permittivity. For any given substance, if you want to get its permittivity value, you multiply the dielectric constant of that dielectric material by the permittivity of what? Free space. So we're going to substitute that here, which implies that the capacitance will now be written as E naught times Kr times A divided by what? D. Let us now substitute here and see what we get. Permittivity of free space is 8.85. We're going to multiply by 10 raised to the power minus 12. Then times the dielectric constant value, which is 7, times the area of the plate giving us 5 times 10 raised to the power minus 4. We're going to divide it by the distance of separation, which is 0.04. In standard form, it's same as 4 times 10 raised to the power minus 2. That gives us the capacitance of this capacitor with this dielectric material mica field to be equal to, if you punch this, 8.85 and then times 7 times 5. Let's say that 8.85 times 7 times 5, then divided by 4. I'm getting 77.4 approximately, then times 10 raised to the power minus 12 plus minus 4 give us minus 16. They're going to add these two. You know, if minus 2 goes up, it becomes plus 2. So you add plus 2 to minus 16, which will give us minus what? 14 farad. Does that make sense? If you compare this capacitance with what we obtained when the space between the plates was filled with vacuum or air per se, as we assumed in the first case, you'll notice that this capacitance is greater than the former. Alright, when there is a dielectric material mica, is greater than when it was air or vacuum. At that first instance, we obtained 11.06 times 10 raised to the power minus what? 14 farad. Then this is what? 77.4. Is that okay? So you take note of that. This is greater than that former, which means that the capacitance with a given dielectric between it, alright, in the capacitor will be greater than when it is air or vacuum. Let us now calculate the energy stored. I'm going to use 1 over 2 CV squared, okay? Which is now going to be 1 over 2 times the C is 77.4 times 10 raised to the power minus 14. I'm going to multiply it by voltage 240 squared. So that's my E is now going to be, that is the energy stored. Let's find out. So it's going to be 240 squared. And then multiply that by 77.4 times 77.4. And then divided by 2. From here, it's giving me 2229120 times 10 raised to the power minus 14 joules. You know, if you still want to move the point from here, 1, 2, 3, 4, 5, 6. It's going to be 2.23 times 10 raised to the power. You move the point 6 times to the left, so you add it to minus 14, which is going to give us minus what? 8 joules. So this is the result when the space between the parallel plate is filled with a dielectric material mica with relative permittivity of 7.